So in this series of videos, we're going to be looking at what are called improper integrals. This is technically a technique of integration, but it's not undoing a rule for differentiation. It's not helping us with antiderivatives. What it is it's helping us deal with infinity when it comes up in integrals. So just starting with the definition. An improper integral is one where either one or both of the bounds are infinite, or there's an infinite discontinuity, a vertical asymptote, somewhere within the bounds of integration. Uh, if you remember when we talked about, when we were introduced to integrable functions, vertical asymptotes cause issues. Other discontinuities, no big deal at all. We can integrate right over every other discontinuity, but an infinite discontinuity is what we call an improper integral, and sometimes we can evaluate it and sometimes we can't. Our general approach to finding these is that we're going to take it from being a definite integral, from being an integral, and make it a limit of an integral, which is already a limit. So since we're doing a limit of a limit here, we're not going to be talking about how the improper integral equals a value exactly, but because it's a limit and it approaches it, we're going to use the words converge and diverge. So an improper integral, if it exists, will converge towards a finite value, or it's going to diverge, meaning it's infinite. So first, we're going to look at if the bounds are infinite. So if the bounds are infinite, this comes in three situations. The first being if the upper bound is infinite. So I can have it set up to be a constant lower bound, infinite upper bound of my function. What I do is I can't actually evaluate this as like a definite integral, because a definite integral has two real bounds. And infinity is not a real number, so it's not a definite integral. So we turn it into a definite integral by saying, okay, let's replace infinity with a variable. I usually use b for the upper bound, and then do the limit as b approaches infinity. I then evaluate the definite integral with a variable in it, and once I've done that, I can then evaluate the limit as that variable is approaching infinity. Alternatively, it's the lower bound that could be infinite, going towards negative infinity. Same approach. This is not a definite integral because negative infinity is not a real number, so I replace the negative infinity with a variable and do the limit as that variable approaches negative infinity. The one that requires the most work is if both bounds are infinite. What I first have to do is split this up into two different integrals. I like to just use 0 as the connecting bound here, but you can use any real number you want. And then they become, I have one where the lower bound is infinite, and I have one where the upper bound is infinite. And so I end up having two limits. So an example of this, if I am looking at the integral from 1 to infinity of 1 over x, I cannot actually evaluate this right off the bat because infinity is not a real number. So the first thing I have to do is change this so that I'm doing the integral from 1 to some variable. Like I said, I like to use a's and b's because I'm used to that with my bounds. This is an integral I can actually evaluate because now it is a definite integral. And then I'll do the limit as b approaches infinity. So I just hold on to the limit, and I'm going to evaluate my integral. So antiderivative of 1 over x is the natural log of x. I do not need absolute values because I'm going from 1 to positive 1 to a number larger than 1. So absolute value is not needed. This is from 1 to b. Plug in my upper bound, plug in my lower bound, and subtract. Well, the natural log of 1 is 0. And so then as b is going towards infinity, the natural log of b is also going towards infinity. So what this tells me is that my limit diverges because it's going towards positive infinity. So this integral diverges. It doesn't exist. The next video will have a few more examples of these so that you have a chance to practice it a bit.